let's go over number one. I have a fast step and a slow step. And let's first of all make an overall reaction. Anything that's present on the left and the right both gets canceled out. That's an intermediate then. It got created and yet destroyed. And so it's not in the overall reaction. It's not something that was present as a reaction, and it's not present in the products at the end. So it disappeared. It's not in the overall reaction. So I have two of those and two of those and one of that. The difficult part is getting the rate law. The slow step is the rate determining step. This is what really governs the speed of the reaction, the rate. So each elementary step, as they're called, has its own rate. The trick here is that the fast step is going to build up CL so fast that this second step can't handle it. So this is going to almost immediately build up a lot of this, and this whole reaction then is going to start running backward. And so in such a short span of time, as no one cares to discuss, this is going to be running left as hard as it's running right. So we're going to put this arrow on there. It's running left also. And remember, we said the rates are equal. It's running left as hard as it's running right. And so that's an equilibrium. Now, the second step is the slow step. And then we can just say that it has its own rate law, and its rate law would be the reactance to the power of the number in front times the K for that step. So here's the rate. The rate for the second step would be the K for the second step times the reactance to the power of 1, because there's 1 in front of here. Here's the problem. I don't like that CL in there. CL is not in my overall reaction. It's not helpful. Let's get this out of here in a mathematically and logically defensible way. We said that this is an equilibrium, in which case this concept of K constant is true. And this is just K for the first step. Some people don't even put the 1 and the 2, but I'm doing it just to try to be extra helpful. K is products over reactants, all to the power of the number in front. So 1, 1, 1 means that all these have power of 1. These are the products over the reactants, and they all happen this time to be to the power of 1. I don't like this. I want this out of here. If I rearrange this, I can solve for CL. And whatever that equals, which is all this, I can put it there. So this goes up, this goes down, as we talked about. And this whole box is a substitute for that. So I'm going to lift this up and put it there. So this is on the top, along with the previous one of the same kind that was there already. And then this is on the bottom, because when you multiply fractions, they kind of just smush together, right? And there's the K1 that arrived, and it is multiplied by the K2. And then the heavy lifting is done, and we are almost finished here. Any constant times a constant is just another constant. If that's 3 and that's 4, then I know that that's 12, and it's always going to be 12. So you don't even really have to keep track of this is 1 and that's 2 and that's 3. Some people just put K and K and then KK and then just have another K, because it doesn't matter, frankly. This times itself is then squared, isn't it? That's the faster way to write that. And this just remains on the bottom. And you're done. You have your new overall rate law. Let's do number 2. I'm going to first make the overall equation by canceling out the two things that exist both on the left and the right. That gives me one of these and one of these and one of these and these and these. And we get that yields this triple one here and one of those. Now I want the rate law, though, the rate equation. And again, the second step is slow. This is my rate determining step. So every elementary step has its own rate law. And in this case, it would be this to the first times that to the first times K. There we go. The problem is that there is no ABC in this law. It's not useful. Let's get this out of here by doing something defensible, mathematical, and logical, right? This is going to build up ABC, much faster than this can take it in. This is going to become an equilibrium by running left just as fast as it's going right, in which case I can say that K is true. So this kind of K is true only for equilibriums, and it's products over reactants all to the power of the number in front, which in this case is all powers of 1. I want to substitute in for this. So let's solve for this, because that's the same thing. These three all go up and are multiplied by K from the first one. We'll mark this number 1 right there, right? And these now are all equivalent to that. I can take this chunk here and put it in there, which gives me this. The K2 falls. Here's the new K1. All three of those times that one remaining. Any constant number is times a constant number is a third a constant number. If this is 2 and that's 10, then this is 20. And there's your new rate law. Let's do number 3. I'm going to cross out all the things that appeared on the left and the right both. Left, right, left, right, left. That leaves 2 of these, and 2 of those, and 2 of those, and 1 of that. The difficult part is making the overall rate law or rate equation. Each elementary step uses just the reactants to the power of the number in front. So this slow step will have the rate law of H2 to the first times N2O2 to the first times its own particular K. There's the K for the second step, and times these. Now, again, the first step is the fast step, and so it will hit equilibrium. It will produce this stuff way faster than this one can use it up. So this will pretty darn quickly, I mean really quickly, be running just as fast left as it is to the right, which means it is in equilibrium, which means I can use this K, this equilibrium constant. And this is always equal to the products over the reactants, each to the power of the number in front. That is a 1, so this is the first power. That is a 2, so this is to the second power. And the brackets means molarity. If we actually used this, we would use the molarity values, but not the actual unit M. Here is the rate law for the second step, right? What I don't like about this is that it has N2O2 in here, and there is no N2O2 in the overall reaction. That's not useful. Let's get this out of here and substitute in. Look, it appears over here, yes? So let's solve for this. Let's push this up diagonally there. This then is equal to that. I can take this and put it in for that. I can put it in for it here. So notice this has become that. Here's the NO squared. There's the K from the first one. Any constant number times another constant number is a third constant number. And these just remain like that. And here is our overall rate equation. Let's do 4 and 5. I'm going to cross out what appears both left and right, and that gives me this rate law when I put these two together. So there are 2 possibilities, either the first one's slow or the second one's slow. If the first step is slow, which is always the rate determining step, the slow step, then I can just take the reactant to the power of the number in front and put it on K, next to K, multiplied by K, and that's the rate law. However, that would be true if I knew that this was the slow step. I'm trying to find out if it's the first step. This is the experimental rate law. This is what I trust. This is just a proposal. If the first step is slow, then this is the rate law, but we know this one's right. And if this one contradicts it, then this is wrong. Okay, so at least this is not the first step. Maybe it works if this is the slow step. If that's true, then we know that the first step hits equilibrium. It's running left as hard as it's running right, which means I can use the equilibrium constant. And it's products over reactants, the power of the number in front. So this will be to the first power. This will be to the second power on the bottom. Then let's do the rate law for the second step, which would be this to the first times this to the first times K. The problem is there's no X2 in the overall rate law. Let's get this out of here. It's not useful. Let's substitute in. I can solve this for X2 by pushing this up diagonally. This then substitutes in for that anywhere like right there. So I'm going to take this block here, put it there. Here comes the K1. There's the X squared. And then any constant times another constant is yet a third constant. And so there is your overall rate law. So in 5, we have something similar. Here's the experimental rate law, and we have two possibilities. This is slower, this is so slow. So let's try to have the first step be the slow step. If that's true, then I can just take, this is 2 of them, right? I can take this to the second power times k, and that would be the rate law for the overall if this is the slow step, and then we can just disregard this one. Does that match the experimental data? Yes, it does. This matches the experimental data rate law, and so this is the slow step, and that one's the fast one.